So I'm very happy to introduce Craig, who's visiting us today and tomorrow. Somewhat delocalized in Introduction and PNS. We'll see. Say again? No, that's fine. We can arrange something. Sorry. So he'll be talking about SCFTs in various dimensions, 4 dimensional things. 4 dimensions, precisely. Sure. Okay, thank you. Yeah, first of all, thank you for this invitation. I'm always happy to come and visit Paris. And one thing you might notice immediately is that the title has rather changed a little bit from the title that I gave a few days ago. But the content of the talk has not changed, so the abstract is the same. Okay, so I will talk about work that I have been doing over the last, probably about the last year, mostly in collaboration with Monica Khan and Jaewon Song, and then later on including Ki-Hong Lee, and then another paper which should come out, I would optimistically say this month, with Matteo Satti as well. So I'll tell you something about this sort of sequence of works, which was sort of inspired by thinking about theories with identical central charges. But I'll explain about why that's interesting now. Click and click. Okay. A little bit of lag. Okay, so I'm going to give you a very, very brief, very broad words of motivation. So first, what are we interested in? So personally, quantum field theory is very interesting. So quantum field theory is a subject which has wide ranges of applicability far outside of even high energy theory. And so a very natural question is to try and understand what kind of quantum field theories are possible. And already that is a rather large but also restricted set of things. So there are a lot of things that you think might be a consistent quantum field theory but are not a consistent quantum field theory, and so on. But one of the problems that we have is that it's generally hard to study an arbitrary quantum field theory outside of what you might call a perturbative regime. So outside of, like, perturbations around some Gaussian fixed point, you don't have a lot of tools with which you can tackle a generic quantum field theory. But one thing which we know very well how to do in sort of physics is that once you start adding symmetries to a problem, you make that problem easier. You make that problem more tractable. And so that's largely the motivation for what we're going to consider doing today. So the first thing you might consider adding is supersymmetry. So supersymmetry tells you that certain quantities outside of, say, some perturbative regime are protected from quantum corrections. But you see that the size of this bubble has now shrunk rather a lot because, of course, there are a lot fewer supersymmetric quantum field theories than quantum field theories in general. Another symmetry which we might add to make our lives easier is conformal symmetry. Conformal symmetry exists at the fixed points between your normalization workflows between quantum field theories. And so you already capture a lot of information about an arbitrary QFT by studying its fixed points. So if we restrict ourselves to exploring the fixed points, we're already getting some good information about the space of QFTs. And again, our bubble has shrunk a little bit more. Okay. So what we sort of want to do and how we're motivated is to study this particular subspace of quantum field theories. Okay. So that was sort of a very brief motivation for why we want to study the objects that we call superconformal field theories and why we can use them as probes of sort of the landscape of consistent quantum field theories. Okay. So how do you actually study a conformal field theory? What do you need to know about it? Well, there are some quantities which you can compute. So in particular, if you take a conformal field theory in some number of dimensions and you put it on some arbitrary curved background, then the conformal symmetry itself becomes anomalous. That is, it's not actually a symmetry of the theory anymore. And the way that it becomes anomalous is measured through the VAV of the stress energy tensor, which is proportional to the Weyl tensor and the Euler density, which are invariants of the particular 4-manifold on which you put the conformal field theory. And there are these coefficients A and C, and these are known as the central charges. Okay, So these are some numbers that are associated to some quantum field theory that measure how badly conformal symmetry is broken when you put it on an arbitrary manifold. Okay, so what did they tell you? Why would you care about knowing these numbers? Well, so if you have two theories which are related by a renormalization group flow, so I have a theory in the ultraviolet with central charges A and C, I have a theory in the infrared with central charges A and C in the infrared, and there exists some renormalization group flow between them, then the result of Komorodsky and Schur, which is known as the A theorem, tells you that this quantity A monotonically decreases along any renormalization group flow. So in this particular sense, we understand renormalization group flows into the infrared as integrating out massive modes, something like this. In this sense, you can think of this quantity A as measuring something like the degrees of freedom of the field theory that you're considering. So in that sense, it's sort of a very physical, observable. And it's interesting to note that there's no equivalent statement for C. Sometimes C predominantly decreases along flows, but sometimes it goes up. So it turns out that just assuming that your conformal field theory is a unitary field theory, something we certainly want to assume, then the ratio of the central charge is extremely constrained. So this is a result due to Hoffman and Maldacena. And what they found is that the ratio of A over C is basically saturated at the lower end by the free scalar field theory, and at the upper end by the theory of a free vector multiple. So I should just emphasize that everything I say today will be in 4 dimensions. Okay.
Sorry, you said vector multiplet, you meant just vector fields?
Just a vector field, yes, precisely. Yes, and please do just jump in with any questions at any time, also on Zoom. I think it will just zero here. Okay. So we wanted to know about adding supersymmetry. And when you add supersymmetry, these bounds become a little bit stronger. So you can have 0, 4, 8, 12, or 16 supercharges in 4 dimensions. And you see that the bounds get sharper as you increase the amount of supersymmetry. So the lower bound is always saturated by whatever the supersymmetric analog of the free scalar is.
I can briefly also ask a question. So you stressed about any renormalization group flow.
Yes.
So does it mean if you pick a theory and then perform any deformation flow to the new fixed point, this is what you mean by any renormalization?
Yes, this is what I mean by any. Yes, precisely. It's a very, very general result, so no assumption that the fixed points are supersymmetric or anything like that. Yeah. So yeah, the lower bound is always saturated by the analog of the free scalar, which is either a free chiral or a free hyper. And the upper bound is always saturated by the free vector with its supersymmetric partners. And you see that once you increase your amount of supersymmetry sufficiently to reach at least 12 or 16 supercharges, you find that actually A and C are forced to be identical. And in some sense, you can see this as saying that you don't have 2 independent multiplets in these theories. You have only a single vector multiplet, so that the bound is sort of saturated on both ends by the same object. Okay. Okay. So now that I've told you a little bit about sort of what quantities you might want to know about conformal theory. Yes.
Something sounds strange to me with this formula is that 1 hyper is twice it's 2 Carl multiplet, whereas the number are the same. So I know it's because it's a ratio.
Right. Precisely. Yeah, so now that we sort of see some of the features and how some of the features might be interesting, let's look at some examples of some theories. So there's a sort of much studied class of examples. These are under the sort of name of the class S theories. They were written down in 2009 by Kyoto and Mornitsky, and they have a certain structure to them, which I will now explain. So you start by taking the 6D 2,0 superconformal field theory of type G, where G is an ADE Lie algebra. So this is a 6-dimensional theory, and it's realized in type 2D string theory as a compactification on a hyperkähler or non-compact hyperkähler manifold, which is just an orbifold singularity. So these are some fancy 6D theories which sort of lack a reasonable perturbative description, but we could still use them to learn about four-dimensional theories by performing a twisted compactification on an n-punctured genus G Riemann surface. So that gets you down to 4 dimensions, and if you choose this twisting correctly, you get something which has 4D n = 2 supersymmetry in 2 dimensions. And I said that you did the compactification on a punctured Riemann surface. What does a puncture mean? A puncture is basically a codimension 2 defect in the 6D theory, and there is some data associated to those defects. So they're typically associated to nilpotent orbits of G, the Lie algebra of the 6D theory, but they can also be associated to more complicated things. Although I will today only really talk about the nilpotent orbit case. So you put all these things together, and what do you have? You have a 4D n = 2 SCFT. And the fact that you have this sort of top-down construction from 6 dimensions allows you to say that a whole bunch of complicated physical features, like S-dualities, things where you go from some strong coupling theory to some weak coupling theory, are actually captured very simply by this construction.
Some on Zoom is still this camera that's being used. Can you check that we're using it?
My camera is on.
Did you select that one?
Is that an option?
Well, it doesn't matter. Just
there's a spotlight. Is that the thing?
not. Yeah, now it's better. Yeah, that's good. Yeah.
Okay.
It will change if you don't.
Okay, that's good.
Okay, very good. Let's try this. Okay, so yeah. So some complicated physical features are captured by this construction, and this is how they are captured. So an n-punctured genus G Riemann surface, if you read the math literature, you find that it has something which is called a pair-Pants decomposition. So the pair-Pants decomposition tells you basically that you can pull this thing apart into a bunch of spheres connected by very thin cylinders. So you can see I've drawn this genus 2 surface here, and you can see that topologically these two things are the same thing. I have 2 holes, and I have 2 holes. So it turns out that if you understand the 3 punctured spheres and you understand how to glue them together, then you understand all of this complicated zoo of theories. So these 3 punctured sphere theories go under the name of Tinker-Toy theories for some reason, and they have been studied in great detail in this series of works by Celticana, Dissler, Trim, Zool, and a few other people. But the point to take home here is that these class S theories is a very broad construction, but you can always reduce it down to a simple set of building blocks with which you can construct more complicated theories. And understanding the building blocks allows you to understand the rest of the theories. So let's have a little look at the landscape of 4D n = 2 theories. So here on this side here, you see the class S theories that we just talked about. And of course, you should visualize this very large box as a very small subsector in the bubbles on the original slides. There are several other constructions. So one construction, for example, is to consider a different kind of 6D theory, one with 8 supercharges, and compactify that on a T2. That can also give you a 4-dimensional n = 2 theory. And sort of this overlap we studied in this paper from last year, but that's not going to be the focus of the talk today. The focus of the talk today is going to be this purple region. So the purple region is theories where the central charges are identical. And there are several reasons why this region is interesting. One of which is it contains entirely the sublocus that has enhanced supersymmetry. So n = 3 or n = 4. And what we find is that there are certain senses in which these theories sort of behave like they have enhanced supersymmetry, even though they do not. Yeah.
So you showed that for n = 4, a = 3, but for n = 3, that wasn't the case. That's entirely containable.
For n = 3, you have to have a = c. It's a slightly different argument because you don't have a perturbative description of n = 3, but you can look at the superconformal algebra and you see that it's also required in that case. Okay. So why might we be interested in looking at this particular subspace of the landscape? Well, first of all, if I come at this from a holographic perspective, then I have some ADS5 times x5. And A equals C typically goes like some order n squared kind of thing in some large n limit, functioning in something like type 2b, etc., etc. And the subleading terms in this holographic construction are basically captured by two quantities. There's a linear in n quantity and there's an order 1 number. And the coefficient of the linear in n quantity typically comes from open string degrees of freedom. So typically you might have some branes in this system and you have some open strings. And these typically contribute to the linear terms. And then there are order 1 terms, and these typically come from like some closed string modes in this case in type 2D string theory. So if you were to see that the two central charges are identical, then it must be true that these contributions both vanish. Okay, it's easy to make this contribution rho vanish if, say, you consider a solution without any branes turned on. But making this sigma, the closed string contributions vanish is a little bit tricky. So in the case of n equals 4 super nils, where you have the ADS5 times S5 as the holographic dual, then there's a very sort of, it's actually not delicate. There's sort of a very powerful cancellation between huge KK towers of different states such that this contribution sigma is 0. So this sort of begs the question, if you have another theory with A equals C, a similar cancellation must occur. And that's it's always interesting when you see large cancellations.
There will also be some 1 over n corrections and so on, right? So you put all of them to cancel at once.
That's right. So you may have to have both things.
Is it easy to see the S5 versus S5 while all of them cancel?
So it's not. It's much more delicate than the n equals 4 case. In the n equals 4 case, what sort of happens is everything cancels order by order. Whereas here, it seems like you have to resum everything and then make it cancel. And then it does cancel, it seems like. So this is something we're working on at the moment. But it's a bit delicate because you're summing an infinite series of KK modes, and then are you taking the right regularization and so on.
Just a question. In principle, you can have A not equal to C if you consider high-level corrections. Your space-time doesn't have the impedance symmetry.
What do you mean you can consider A is not equal to C? I mean, the generic case is A is not equal to C.
Okay, so you only consider A for A.
Yeah, exactly. In fact, yes, exactly. What I'm trying to motivate here is actually that if you want to consider the case equals C, you have to do a very, very special regime, as you say. Yeah.
I think I just used the first part of the problem. I'm really not sure this exploring the whole landscape of A versus C or this.
Yeah, this is just, we're looking at this very special subsector. Okay, thank you. Okay, and there are a bunch of other interesting quantities in conformal field theories which are controlled by the C minus A difference. So for example, you see that in the Carnot limit of the superconformal index, the index is proportional to C minus A. So the exponential behavior of the index disappears when C is equal to A. It also appears in the entropy viscosity ratio bound, which I won't say too much about. Also in the current gravitational anomaly and the single trace higher spin gap for large n, as studied by a variety of people on the site here. I won't say too much about any of these points. I just want to sort of make the point that this quantity C minus A seems to control interesting things. And typically you see some kind of special behavior, most best exemplified by the superconformal index point where the exponential behavior drops off for theories with A. Okay, notice, nothing that I just said is really specific to a 4D n equals 2 theory. I could equally have talked about a 4D n equals 1 theory. I could equally have talked about 4D n equals 0 theory, but then I can't make any progress. So a little bit later on, we will consider the generalization to 4D n equals 1. Okay, so one of the reasons I'm motivating the class X construction is that you can break everything down in terms of some building blocks, and if you understand the building blocks, then you're doing well. So for this A equals C region, we can think of some quite natural building blocks. So first, there's a theory which was under the name of DPG. These are some non-Lagrangian Argyres-Douglas type theories. They have fractional Coulomb rank scaling dimensions. and they're generically non-Lagrangian. They've been studying sort of this series of works over the last 10 years or so. And these theories do have a class X description, somewhat explaining why I introduced the class X construction. They are associated to two punctured spheres, where one of the punctures is so-called regular maximal puncture, which just carries the flavor symmetry G, which is why there's a G there. And the other puncture is an irregular puncture, which is actually why this thing is stable, because if you recall the dimension of the moduli space of a two-puncture sphere, it's supposed to be -1. So that might be problematic, but that's sort of captured by the fact that this is a so-called irregular puncture. Okay. And these theories typically have a G flavor symmetry, but they can have additional flavor symmetry coming from the irregular puncture under these kind of conditions at the side here. So these are kind of GCD type conditions related to divisors of things, which we'll see becomes a bit relevant later on. Another different type of 4D theory that you might be interested in is sometimes known as GG conformal matter by Delzotto, Heckman, Tomasello, and Vafa in the 60 case, and with the obvious connectification to 40. So this theory is basically just a strongly coupled generalization of the bifundamental hypermultiple, right? So when G is SUK, then it's just a bifundamental hyper. But what happens if I take G equals EA? What does a bifundamental hyper mean in that sense? Well, the answer that we would say would be it's whatever this strongly coupled conformal theory is. And these things also have a class S description. So they now have two regular maximal punctures. So they have G times G flavor symmetry. And then they have one other puncture, which is associated to the subregular nilpotent orbit of G. In an unfortunate clash of nomenclature, the subregular here is a regular puncture, and the regular is not, this regular is nothing to do with this regular. This is a very unfortunate, but something we just have to live with. Okay. So we could ask ourselves a question. We could consider either n equals 2 or n equals 1 gauging of all G flavor symmetries of a collection of these building block theories. And we can see what we get. And obviously, you know, we're going to get some theories with identical central charges. Otherwise, I wouldn't be emphasizing it so much. But let's just phrase it as some kind of classification problem. And we'll see that there's sort of a nice result in the math literature. So how can we gauge together all G flavor symmetries of a collection of DPG and GG conformal matter such that we get an n equals 2? So it's very restrictive. I don't know if that's surprising or not, probably not very surprising. Okay, so how do you actually, what computation do you actually need to do? Well, the flavor central charge of the G flavor symmetry of DPG looks like this. It's 2p minus 1 over p times the dual Coulomb number. Conformal matter has two copies of G times G, and they both have the same flavor central charge. That's 2 times the dual Coulomb number. And if you want to gauge these, if you want to gauge some flavor symmetries together in such a way that you get a conformal theory, then you need that the one loop beta function associated to that gauge node vanishes. And this is equivalent to saying that the sum over all of the flavor central charges that you gauge is equal to 4 times the dual Coulomb number. 4 times the dual Coulomb number comes from the vector multiplicity of now introduced. Okay. So let's do a slightly simpler case first. Let's assume that there is no conformal matter and just copies of these DPG theories. You take n of them. And the constraint for vanishing of the one loop beta function of the gauge coupling of this gauge node is given here. And it's equivalent to this sum here. Okay. And if you stare at this sum hard enough, you see that there are not very many solutions. In fact, there are only 4 solutions to this, which is when the PIs are either all 2s, all 3s, 2, 4, 4, 2, 3, 6. Yes. So okay, well, one also has to check. But yes, they are. It's a non-trivial statement, but they are. Yes. And I just point out, by the way, that the reason we include p equals 1 is because d1g is defined actually to be the trivial. So this is why this greater than or equal to 2 condition comes in. Okay, so there are 4 theories. Okay, what about including conformal matter?
Trivial is free or is nothing?
Nothing, really nothing. I guess the better way of saying it is that the theory is only, the construction is only defined for p greater than or equal to 2. Yeah. So
What is there is that equals C or?
Okay, good. So these theories here will sometimes have A equals C. It depends on a certain GCD-like condition.
Before.
So yeah, similar to exactly before.
But it also depends on G.
Oh, there's just a 4 times the number of proteins. Okay.
Yes, yes. Yeah, so basically the GCD condition basically tells you that the dual Coxeter number of G and basically the largest PI must be co-prime. And then you have A equals. But I'll show you that in just a moment. So I want to include conformal matter to sort of feel out this kind of classification problem that we're doing. And to do this, we're going to first take a brief digression back to, I guess, 1996, which is, what is the world volume theory that lives on a bunch of D3 brains probing an orbifold singularity? You know what the answer is. It is an affine quiver gauge theory. So you see that these are just, there's the A series, D6, D7, D8, where each of the gauge nodes is just SUK gauge theory, where K is the number of D3 brains times the Dynkin label of that gauge node. Of that node, Dynkin node. Okay, so this is an old result, but there's sort of a natural question. What if you wanted to construct such quivers, but where you didn't talk about SUL, SU2L gauge nodes, but you talked about E8 gauge nodes? What would be the generalization of this? And there are 2 obvious questions if you're going to propose such a generalization. The first one is, what is the generalization of a bifundamental hypermultiple? You should be able to guess what this is, because I kind of told you 10 minutes ago it's going to be the conformal matter theory. More detailed is, what is the generalization of this kind of thing? So, you have SUL next to SU2L. That's kind of strange. What's 2 times E8? Or SU-E16, what's going on? Okay. But in part, the reason why you don't need to deal with this is because when you generalize from SU to just some arbitrary ADE type, then you end up with these non-Lagrangian DPG theories being involved. So you never have to worry about Lagrangian quivers that have this kind of ramping behavior. So I'm going to put this on mute because it's kind of annoying. So please bear with me for 1 moment. Okay. Okay, great. Okay, so once you use these generalizations that I just mentioned, you could write down these 5 different configurations. So in this first one, I've just replaced the SU nodes with G nodes and replaced bifundamental matters with copies of conformal matter. That's a reasonable generalization, one might say. Here, what has happened is we've replaced the SU2L nodes, right, which were here, the SU2L nodes in the middle. We've replaced them with Gs, and we've replaced the SUL nodes with D2Gs. Okay, why? Well, first sanity check is that if you let G equals SU2L, then D2 of SU2L is just a single SUL gauge node. So it always reduces to the correct thing in the SU case. But I guess you can't quite see the end of the sentence at the bottom here, but these are exactly the configurations of conformal matter and DPG theories which solve the classification problem which I just proposed. So how do you gauge all of these things together such that it's conformal? These are the only solutions. So in that sense, this you would certainly call this an ADE type classification.
So in the previous slide, you still have LD3 branes on two gamma. So what's the construction for those guys?
Right. So I don't know what the brane construction for these things is.
So for instance, does it work if you put an orientifold, then it gives you this for G equals D type?
So good. So if you put the orientifold, where is it? So what happens if you put the orientifold here is that you get basically affine quivers with alternating SO and SP gauge nodes. And it also works if you take just these D2 theories of G equals SO, then they have these, then they occasionally have these Lagrangian quiver tail expansions in terms of alternating SOSPs. So you also recover these. Yeah, but in the general case, I don't know, some D3 brane description. And so the orientifold case is a good point, because in the orientifold case, you might want to think of it as saying that you have sort of half a D3 brane. And in these cases, the E6078, you can sort of morally think of it as having a third, a quarter, and a sixth of a D3 brane. This is not very convincing. So whatever I'll talk about this a little bit later on, but whatever the brane description is, it at least seems to involve something like fractional branes. So how you understand that is sort of a question.
Sorry, what is the D group? Let's see.
Good. So for DPG, it's just a flavor symmetry.
So they always just favor another.
Yes. So DPG always has a flavor symmetry, which is G. It might have more flavor symmetry, but it always has a flavor symmetry, which is G. Now, yeah. So now we consider like gauging that flavor symmetry. And really, like here, for example, we consider gauging the diagonal of 3 flavor symmetries of 3 copies of D3G. Yeah. I shouldn't say that DPG has a gauge node, but I sort of always mean that you gauge the flavor symmetry of it. Yes, that's right. Okay. So, and this I will also explain here. So there is some particular choice of ADE Lie group which describes the structure of the quiver. So AD6078, and there is some particular choice of ADE Lie group which describes the central gauge node or the nodes that are G here. And so we have a bunch of theories that are labeled by a pair of ADE Lie algebras. Okay, so that's quite a nice solution to this rather esoteric problem we kind of proposed of how to gauge together a whole bunch of sort of perhaps somewhat random looking 4D SCFTs, and the answer is given in terms of some ADE groups. That's always very pleasant to see. So let me tell you about some interesting features of these things. So the first feature is obviously going to be the one that I highlighted in the title: when do these theories have identical central charges? So if there's no conformal matter, which basically restricts yourself to the D4E6078 case that we talked about originally, these are the ones corresponding to the 2222 and so on. And if the greatest common divisor between the dual Coxeter number and the highest core of lambda is 1, then the theories have A equals C. So one thing to point out, by the way, is that if this what does this GCD condition tell us? If this GCD condition is not true, then what it means is that at least one of the DPG theories appearing here is actually a Lagrangian quiver. So this happens exceptionally, basically, when P divides the order of G. And once it's a Lagrangian quiver, you have enhanced flavor symmetry because you have, by fundamentals and so on. So it's precisely saying, this condition is precisely saying that they have A equals C when everything remains as non-Lagrangian as possible. And indeed, A equals C takes this actually very evocative form. I won't talk about this, but this particular form here kind of looks like something you can obtain from quotienting a 5-sphere and some supergravity description.
Is there a simple way of computing A and C for this gauging procedure once you know the ones from the constituents?
Yes, precisely. So it's more or less just adding up the ones from the constituent ones and then taking into account the contribution from the vector multiplet that you introduced. So for something like the central charges, it's very nice because it's very easy to compute the things with the gauging. In a few moments, I'll show you some indices where to compute them you have to basically take an integral over the building blocks. But for A equals C, it's very nice.
The index knows about C minus A, as you said.
Yes.
Can you read off A and C separately?
So I don't think you can read them off separately from the index. So one interesting thing you see from the index is that the coefficients grow very slowly, which is what you expect because the exponential behavior is captured by C minus A. So you see this really in great detail. Unfortunately, I don't think I have an example of the slow growing coefficients on the slides. That's a bit unfortunate. But I'll have some examples later. Yeah, so can any of these theories be realized inside of class S? Well, it's not obvious. So these theories typically involve some kind of multivalent gauging. And so think of this as like the E6 hat theory. So you have 3 copies of D3G. Each copy of D3G is associated to a 2-puncture sphere, and each regular puncture is associated to the G flavor symmetry, and you have to gauge them all together. But this thing, whatever I've drawn here, this is not a pair of ants decomposition of a puncture Riemann surface. So this certainly does not look like it belongs to class S. But that's slightly too fast. So there is actually an alternative description, which is something which will appear in this paper with Monica, Ki-Hong, Matteo, and Jaelong, hopefully this month, which is that there's a particular 3-punctured sphere, this 3-punctured sphere here. The technical details are that it's of type A2N with 2 twisty null punctures, but you don't need to know that too much. And this theory was studied in this paper here, and what they found is that this is actually a product theory. This 3-punctured sphere here, ignore the other side. And the 3-punctured sphere is a product that is just 2 copies of D2SU2N plus 1. Okay, but how did we construct the D4 hat theories that I just talked about? We gauged together 4 copies of D2SU blah, blah, blah. So I can take 2 of these 3-punctured spheres, I can gauge them along a cylinder. And it turns out that this gauging exactly corresponds to gauging the common SU flavor symmetry of 4 copies of D2SU. And so this theory is actually the D4 hat SU2N plus 1 theory. But this description that I've just given is not related at all to the description in terms of 2-punctured spheres with 1 irregular puncture. So understanding sort of how this description is related to sort of the description via gluing the building blocks is, I think, an open question. And there might be something interesting to understand there about sort of what happens with colliding irregular punctures or something like this. But this is something that we're currently investigating. Okay, so I told you which theories have A equals C. And I told you which theories have the class S description. So let me see if I can tell you something else about this sort of interesting collection of theories. So the Schur index is basically defined as a certain trace over certain operators inside of the moduli space. And you know what the Schur index is for DPG theories if they have no enhanced flavor symmetry. This was worked out by these authors on the far side. And it has this rather simple expression here. I won't explain the notation, but some simple expression.
That delta minus L is dimension minus R.
Yes. Yes, precisely. Okay, so the index of the gauge theory, so to perform the gauging in the index, basically you have to take an integral over the fugacity of the introduced vector multiplet. And then 4 copies of the index of, let's be careful not to touch, 4 copies of the index of D2G. And if you plug this in and massage it around a little bit, you see that the end result is that it's this integral here. Okay, does this integral look familiar? Does this coefficient look familiar? I don't expect anyone to say yes, but it does. So for all of the other cases, not just this D4 hat case that I just discussed, you can always rewrite the Schur index in this way. So in terms of this sort of combination of coefficients here, written in terms of, again, the highest core root of the Dynkin diagram associated to get them. So yeah, that's either 2, 3, 4, or 6. And on the right-hand side, as you can see, this is just the Schur index of n equals 4 supergang mills where you've rescaled the fugacities somehow. That's weird.
So the data of gamma enters only through alpha G, alpha gamma?
Yes.
So for any G, for instance, it doesn't depend.
Yeah,
that's right. It doesn't depend.
That's right. That's right. Well, no. Well, okay. That's not quite a fair statement because here I have to restrict myself only to the D4, E6, E78 theories because I want to use this formula for the index of DPG, and that only holds when there's no enhanced flavor, which means you have to be in the
only for those star shapes.
It's only for the star shape, exactly. Okay. So the index of n equals 4 supergang mills looks like this thing. And from the n equals 2 perspective, n equals 4 has an additional n2 flavor symmetry. It's this guy here I've called X. And you see that, to recover the indices of the gamma hat G theories, you just set these fugacities Q and X to be some scalings in Q. Okay, what's going on? Is this some special structure to do with, like, when you have ABC, you have some structure like this? That's why n equals 4 has it in these theories? I'm not going to answer this question, but it seems like an interesting structure.
So can you make an equivalence at the level of algebras?
That is exactly my next point. So in the specific case of E6 hat SU2, there exists a gradient vector space isomorphism between the vertex operator algebras for n equals 4 supergang mills and for this E6 hat SU2 theory. So for this E6 hat SU2 theory, the vertex operator algebras the Fagin and Tipudin A6 algebra. And Wikin and Nishinaka, they construct explicitly this isomorphism between this and also the algebra of n equals 4 supergang.
So how do you understand that the growth of the coefficients is so slow, even for n equal to 48 mills? Usually for algebra, you expect exponential growth.
Yeah, so
this is a show index that can be considerations.
Exactly. So there is some, okay. So it's actually very special to the Schur index that you see this very slow growth. So you can compute some other objects, like I'm going to talk about some Hall-Littlewood indices in a few minutes, and these grow much faster. So this is actually something we're also looking into a little bit further, is sort of how to understand the chiral algebras associated to the other theories, which, okay, I don't know, I would love to have a big dictionary of non-unitary vertex operator algebras where I could look up these things, but I'm not sure this exists so much.
So how can you know something about the vector space of all operators? From my understanding, the only thing that's understood about those theories are just indices and things that only know about the protected sector.
Yes.
So I would expect to know only about the
okay.
It's not all operators.
Right. So so here we're really talking about a certain protected subsector. This is like this chiral algebra subsector of Rastelli and the collaborators. So this is still a protected sector. Indeed. Okay, here's another fun sort of thing that you can see by looking at the Schur index. So you can actually explicitly perform the integral over the gauge group for sort of sufficiently small g, and you can compute the index explicitly. So this is for d4 hat issue 7, and these coefficients do grow slowly. Because it's issue 7, they still look like they're growing reasonably quickly, but they are growing slowly relative to what you might like exponential behavior like you might expect. So do these coefficients look familiar? I think you have even less chance of recognizing this. But there's a wonderful service called the Online Encyclopedia of Integer Sequences. And in the end, what you find is that actually for all SU2k plus 1, the D4 hat theory can be written in this sort of very simple form. And this object here, this AK, this is called the MacMahon generalized sum-of-divisor function. So this was written down in some number theory papers in 1921. It was exactly 100 years before we published this paper, which is kind of cute. And basically, if you take the k equals 1 in this sequence of functions, it really just becomes a sum over the divisor function. So in this sense, it is a generalized sum of divisor function. And perhaps it's a little surprising that this is sort of randomly popping up in sort of this sequence of theories. So the Schur index, as we know, is the character of the vertex operator algebra of the theory. And we would expect this to be quasimodular. And in fact, there was some nice work from not too long ago, I think maybe 2007, by Anders and Rose, where they proved that this MacMahon generalized divisor function is in fact quasimodular. So this is kind of a nice thing to observe.
Is it also some property of the n equal to 4 Schur index when you specialize the divisor?
So exactly. So if you were to study the n equals 4 index, you would study the full sequence of chiral algebras for all values of n, for say an SUN gauge group. But here, because of the way the relation works, it's only between the odd, like SUN odd. But then indeed, this is also a feature there. And in fact, the way it works is basically this squared is no longer there, it's just a q, because you take the n equals 4 index and you square this is a 2, so you square this. But yeah, exactly the same for n equals 4 with odd gauge group.
So what about the even cases? Do you also have a formula?
No. So well, we didn't really look at it, but for the even cases, these theories are Lagrangian equivalers. In fact, they're just the affine D-type Lagrangian equivalers. And then I think you don't have something as nice as this. So it's a little strange. Unfortunately, it was only for the D4 type theories and not for the E6, E7, or E8 type theories that we were able to find these kind of known sort of analytic functions. Okay, so let me now just extend the story a little bit for a few minutes. We talked about n equals 2. Now let's talk about n equals 1. N equals 1, unsurprisingly, is much harder. So first we have to rephrase the question. How do we gauge together all G flavor symmetries of DPG and GG conformal matter such that the result now doesn't need to be conformal, it just has to flow in the infrared to something which is conformal, and we want it to be n equals 1. So this is much less restrictive than n equals 2, but still somewhat practical. So since I've kind of talked a lot about theories with identical central charges, let's sort of start focusing on the cases that are likely to have that. So we'll consider no conformal matter. Okay. So again, we have something like this, where now the gauge node is an n equals 1 gauge node instead of an n equals 2 gauge node. And the gauge coupling is asymptotically free if you satisfy this condition here. You see the difference is basically that, well, first of all, this used to be a 2 and it's now a 3. And this used to be an equality and now it's a greater than. If it is still the equality, it's conformal n equals 1 gauging. But I don't want to talk about that today. And all solutions of this thing look like this. There's a lot of them. And you see that there are also infinite families of solutions, right? So when I write all ones, that means no theories, and then I have a P5. P5 means it can be any integer greater than 2. So there are a lot of solutions. Great.
Sorry, I see some P equals 1 in your
Yes.
classification, but this was trivial theories.
That's right. And this is just my shorthand so that I can write the table as everything with 5 entries. So the first one really just means a single DPG with any. Yeah, exactly. Okay, but not all of these gaugings necessarily flow to an infrared interacting SCFT with A equals. So one has to first of all use A maximization to determine the superconformal symmetry. And then one can check that as one sort of flows into the infrared, that no operator crosses the unitarity bound in terms of this superconformal symmetry as you get there. So if that happens, then that operator decouples. And if that operator decouples, typically it's removed from the theory in such a way that it breaks the C minus A. Yeah, you have to add some flipper fields and so on. So this is a process which one can do, and we did it in this paper with Monica, Kihan, and Jayon. And you find that actually almost all things do flow to an interacting infrared SCFT with A equals C. So this one is in fact ruled out. You cannot have one DPG, it just flows to some free theory. And also when you have only 2 DPGs, one of them must have its P greater than 2. So these constraints are not quite as restrictive as you might have immediately expected. Okay. Is there anything else here? But that was just without conformal matter. Say I want to do the full problem. Previously, to get like an ADE type classification, we had to include both conformal matter and DPG. What if we do that in the n equals 1 case? Well, the thing kind of blows up. Because you can see that I've written all of the ones here with either 2 or 3 gauge nodes. And you can see that you start getting triangles. And now that you can get triangles, you can kind of start tessellating the plane in all sorts of different ways. So these things now grow much more rapidly with the number of these things. So I could propose a question. Does there exist some classification problem, some generalization of ADE, for which this is the answer? I'm not sure whether that's something which is known, but it's certainly an interesting question.
So we have the C1, C2,
Yes.
any other conformal?
So this is basically a shorthand. So C1 is any collection of DPGs. So for example here, this formal gauging with C1 is like the 4 options we studied before. So basically I can take this configuration here and I can attach 4 D2Gs on this side, 4 D2Gs on this side, 4 D2Gs on this side, 3 D3Gs, and so on.
You can also attach another of those conformal matters.
That's right, but these ones I've tried to draw separately, I think.
Except you stopped at 3 gauge nodes.
I tend to stop at 3 gauge nodes, exactly. Just because it grows so fast.
So for instance, because you said you could tessellate the things, then
Yes.
I'm trying to find one which you can do. So I guess the bottom one, the triangle, can you attach another triangle where you will C2, and then you can really tessellate the plane, or because if you have to put some DPG there, then it will stop.
Take an hexagonal, I don't know if you can build it from these, but take an hexagonal lattice with gauge nodes.
So then
everywhere,
hexagonal has
full matter. No, that's why I took hexagonal lattice and not triangle. So each node has degree 3.
Yeah,
And that's
exactly, yes.
maybe the details of what classification it is, they should.
Indeed. Yes. Indeed. So the conformal matter, the Flavor central charges are 2 times the dual Coxeter number, and for conformal n equals 1 gauging, you need 6. So everything with degree 3 works. Exactly. Another thing you can do in the n=1 context is you can actually also talk about adding matter. So I just talked about conformal matter and DPG, but I could also ask, what if I am allowed to add some weakly coupled hypermultiplets to the central gauge node? It turns out you can, but it's also very restrictive. You can add either 1 or 2 adjoint chiromultiplets and still have a theory with identical central terms. Actually, you can also add 3, but that gives you the conformal manifold n = 4 super indices. So maybe that's less interesting. So if you add 1 adjoint chiromultiplet, this basically just gives you an SCFT that lives on the same conformal manifold as the 4D n = 2 general series. And if you add 2, it's very restricted. Then you have 1 DPG, or you have 2 copies of D2G, and these are the only theories there.
So these are enhanced supersymmetry then these are the conformal manifold.
Right. So there are points where the supersymmetry enhances to n = 2. Exactly. Okay. Okay. So this was my original title. And I changed the title because we're approaching sort of the end. But I wanted to tell you a little bit about some nice result in this paper that should appear very shortly. So we talked about computing the Schur index. Now let's talk about computing the Hall-Littlewood index. So the Hall-Littlewood index basically counts contributions from multiplets, which go under the name of the b hat multiplets and the d multiplets. And this is something that you can compute from the class S perspective. There's this TQFT approach by these authors here, and you can compute it. So let's just consider an example. Let's take this D4 hat issue 3 theory. Computing the Hall-Littlewood index gives you this thing. And the first thing you notice is that there are some negative coefficients. Okay, so that's not necessarily a problem.
Yeah, you replace Q by Q.
Yes, here I use tau instead of Q. Exactly. So they're not the same thing. So if I compute the full superconformal index, like the n = 1 index, and then I have 2 different limits, the Schur limit and the Hall-Littlewood index, Hall-Littlewood limit. One of them I parameterize by Q, one of them by Exactly. But this D4 hat issue 3 theory, we said can be realized by some genus 0 class S theory, right? Which is this thing here. Just to remind you, but now let's go back. So there is a conjecture from this, I think, 2012 paper of Gaudet, Rastelli, Razamat, and Young that any class S theory of genus 0 has a Hall-Littlewood index equal to its Higgs branch chiral ring. So a Higgs branch Hilbert series. So this is kind of nice when this conjecture is true, because you can compute the Hall-Littlewood index. That's a computation that you know how to do, and then you learn something about the Higgs branch. That's something that is more difficult and you want to know. And this statement, you can see just by looking at this table here, basically boils down to the fact that there are none of these D-type multiplets. If these multiplets are missing, then the two things have contributions from the same multiplets, and so they aren't the same. But the Higgs branch is a hyperkähler manifold, and the Hilbert series of a hyperkähler manifold cannot have negative coefficients. So that seems problematic. And in fact, we can compute the Higgs branch Hilbert series.
The Hilbert series should never have negative coefficients. It's not multi functions.
Yes, indeed. It doesn't depend on hyperkähler. Indeed. Indeed. So you can compute the Higgs branch Hilbert series actually directly. In fact, in this computation, it's really done directly by counting holomorphic functions up to x and d term constraints. Although in other examples for different theories, you have to use a bit more less brute force methods. And of course, there are no negative coefficients, exactly as you expect. So that means that this D4 hat issue 3 theory seems to provide a counterexample to sort of this conjecture. And in fact, the key point here is that this theory has 4 twisty null punctures. And in fact, it seems very generic that when you have more than 4 twisty punctures, you have negative terms in the Hall-Littlewood index, and it's thus different from the Higgs branch Hilbert series. So we made a conjecture in this upcoming paper that If your class S theory is associated to genus G in real surface with at least 4 Z2 twisted punctures, then the Hall-Littlewood index is different from the Higgs branch series. So we compute actually both sides of this, the Hall-Littlewood index and also the Hilbert series of the Higgs branch from for a whole variety of theories. Often we have to take advantage of sort of 3D mirror symmetry to understand the Higgs branch Hilbert series in terms of the Coulomb branch of the mirror and so on. So we put this through some sort of sequence of checks, and this seems certainly to be the case. So it seems that in the previous work, they sort of maybe were not thinking about sort of large numbers of twisting punctures, and so this is sort of some generalized conjecture. Okay. Okay. So let me just conclude since I think I'm out of time. So we constructed some broad collection of truly n equals 1 and n equals 2 SCFTs with exactly A equals C. I emphasize truly here because what often happens is that you think you constructed something with A equals C and n equals 1, but actually it has enhanced n equals 4 supersymmetry. And these theories form a generalization of the affine quiver gauge theories that have been around for a long time from D3 brane poking orbifolds, and they have some intriguing connections to n equals 4 superunions. And I think there's lots to work out on that connection. So let me give you just a few future directions. So what are the supergravity tools? This is the obvious question. Why do the higher derivative corrections all vanish, or cancel off each other? In terms of the affine quiver gauge theories, it looks like these things involve fractional D3 branes. Okay, I should even put this in quotes because, well, what does that mean? Is there a D3 brane world volume interpretation of these A equals C theories, similar to their friends when they are in fact the affine quiver theories? Okay. So these theories have a lot of relevant and marginal operators. So do these things trigger flows to some new sequence of interacting SCFTs? Do these theories preserve A equals C? In fact, the answer to this is yes. This is another upcoming paper. So you can study sort of superpotential deformations of, in this case, this theory here, one copy of DPG, where you gauge the G flavor symmetry with 2 adjoint chiral multiplets. And this analysis is very similar to the kind of analysis that was carried out for something like adjoint SQCD by interligated Wang in the early 2000s. So you get this sort of landscape of theories where you turn on superpotential deformations, you get some new theories, and generally, in fact, these theories preserve A equals C under these superpotential deformations. Okay. And finally, one sort of high statement, which is that 60 SCFTs are a very powerful approach to constructing high dimension SCFTs. So in 3, 4, 5 dimensions, coming from a 6-dimensional perspective is usually very helpful. So are there some direct 60 origins of these theories? So there were, what we did is we started with the 60 origin of the DPG theory, the 60 origin of the conformal matter theory, and then we gauged them in 4D. So is there some perspective whereby we can understand these directly in some 6-dimensional perspective? And does that provide us some new insight? That's something that is at least always in the back of my mind. Okay, thank you for your attention. Yeah.
Thank you, Craig. Any further questions? Maybe from online, don't hesitate to unmute yourself and ask questions. With the setup, we cannot see you very well. Yes.
So, yeah, maybe I missed it, but you started from this DPG and Conformal Matter, but then you claim that it's either all n equal to SCFT is A equals C. Why do you start from these 2 blocks and not from them? What's the claim exactly?
So it's certainly not exhaustive. In fact, in this paper, which one? In this paper here, we also find a whole bunch more of A equals C theories by also studying these twisty class S theories. So it's more that they seem to arise ubiquitously constructing from these building blocks. In particular, everything sort of depends on this kind of GCD-like condition, which, yeah, such a condition always kind of feels like a kind of number theoretic kind of connection. So in that sense, it made sense to study this. But indeed, there's much more. And one other thing to say is that you could take the DPG theories and you can generalize them to something called the DPVG theories. And you can run exactly a similar construction. And also you find there are some gauging conditions which give you theories with A equals C subject to similar GCD conditions. We haven't done it in detail, but we looked at some examples. You can do this generalization. Yeah. So, yeah, this is just in this picture at the start, I could draw a little box inside of the purple and surrounding the green that, yeah, contains the theory software.
So if you consider the three branes that can be of three singularity, you can tell when they have the need to arbitrary with A equals C.
So you often run into problems with understanding whether or not there are actually ones floating around this theory, which messes up your A maximization kind of things. In principle, if you can do the A maximization and work out the infrared R charge, then yeah.
Do examples of the class of toric can be of threes, which we need for this class.
So there are examples of, let me see. So we didn't study them, so I don't want to say too much, but I've been talking to some people who have studied sort of similar things like hypersurfaces for the n equals 1, they do Carta, Sandomino, and so on. And they say there are examples of A equals C theories there, and that they are not examples of the kind of theories that we find here. Typically, their central charges look a little bit different.
The kind of queries and groups that you find out.
Yes, exactly. So the n equals 1 case, I definitely think needs to be sort of like understanding what kind of things can arise and how you map this to some other construction is something we should do.
For the n equals 1 case, so A has been calculated by A maximization.
Yes.
It should be very surprising for A to be equal to C at the end of this process, no? I mean, how come you get so many solutions?
Yes, so this was actually quite remarkable. So I didn't. So there's a short proof where basically C minus A enters in two different ways. In one way, it enters in the anomaly, like the trace R. I guess RGG or RGG. So it enters in the trace RGG anomaly, which must vanish because you gauge the G. And it also enters in the trace R anomaly, which is the one that we're thinking about here. And it turns out that basically, as long as the trace RGG anomaly cancels, then the C minus A contributions in the trace R anomaly also cancel. So it follows from anomaly cancellation. I probably could have had a slide on this, but it's like a short argument. It's in the paper.
So this relation to the Schur index of chemical form theory, I understand correctly that basically the A equals C theories came in as a consequence of an underlying N equals 4 structure within this entity. Is it the way to think about it?
So yes, I would think of it this way. So I would think of it this way in the sense that the underlying N equals 4 structure you mentioned seems to be like the existence of this gradient vector space isomorphism between the VOAs. So I would think of understanding it in this way. And I think I should point out that only in the Schur sector is sort of this relation between the index of N equals 4 and the index of these theories true. So if you look at the Hall-Littlewood index, for example, you don't see any immediate relation with the Hall-Littlewood index of n equals 4. So that indicates it's something very much related to like the chiral algebra. But yeah, it seems like the chiral algebra inherits, or A equals C theories have some common chiral algebra structure. Yeah, which is somehow related to this vector space isomorphism.
This graded vector space isomorphism is not an isomorphism on the
No, it's weaker, that's right. Yeah, they are different VOAs.
So is it expected still that having the same VOA means you have the same theory? There was, I think, some hope initially of getting the statuses.
Well, I can't think of the examples immediately. I suspect the answer is no. I expect there are known counterexamples of involving things like discrete gauging or these kind of things.
Almost doesn't count,
right? Well,
okay.
Yeah.
Yeah, but what is perturbative equal to single non-perturbative?
Well, discrete gauging restricts the set.
Okay, so they were only single non-perturbative.
Well, you see what you have available as pieces of your experiment.
I mean, the local operator spectrum is different, so you should be able to compute. There should be a scattering experiment you can, in principle, do to observe this. No, sorry, I take it back. I take it back. It's not.
You will just observe that you're built from these composite even operators, but and you never see all the operators, but you will never check that. You will never be able to test it.
Indeed, the dynamics are the same. It's just the operator spectrum.
Which you have, if the zeros are the same, then at least the Higgs branch of the arrays is
right.
It's associated varies.
I'm still not sure about that, because I can take two different theories with the same Higgs branch, namely the trivial Higgs branch, and these theories have the same VOA, trivial VOA, but they're different theories.
Yeah, that's why I said the Higgs branch is the same.
Right, sure.
Okay,
fine. Yeah, okay.
So maybe we can continue this more technical discussion over coffee. Let's thank Craig. Thank you.